Hello, my name is Ben Myatt from Kindeva Drug Delivery. I am presenting this work undertaken with my co-authors, Steve Stein and Barzin Gavtash, on plume temperature measurements of current and future low GWP pMDI propellants as measured in an anatomical throat geometry. Our industry is embarking on the next phase in propellant usage, akin to the CFC to HFA transition, as new, environmentally friendly propellants are investigated. The search for propellants with lower global warming potentials than HFA 134 and HFA 227 has led to research into new low GWP propellants, such as HFA 152 and HFO 1234. These propellants all have differences in physicochemical and thermodynamic properties. During the CFC to HFA transition, the plume temperature of a pharmaceutical spray was identified as an important factor in terms of patient acceptability of new products. The so-called cold freon effect was reported as being a forceful, cold blast of liquid propellant and vapor impacting on the back of the patient's throat, causing interruption in patient inhalation and inconsistent dosing. Gabriel, Stein and Velasquez reported temperature measurements of CFC and HFA inhalers in 1999. CFC-based sprays were found to be colder than the new HFA products. Patients using CFC and HFA products during the transition initially preferred the CFC products, with feedback suggesting that the cold freon effect indicated that they had received their dose, whereas the lack of the effect with HFA-based products elicited doubts. Given the history of the cold freon effect, the plume temperatures of new low GWP propellant sprays are one important factor that should be considered when developing next generation low GWP pMDI products. The plume temperature of these propellants and their potential effect on patient feel and acceptability is currently unknown. In recent years, improving in vitro testing methods and equipment has been a key area of development for testing of inhaled pharmaceutical products. With recent efforts to improve the relationship between the data generated in the lab and in a clinical setting, the in vitro-in vivo relationship being one of the main drivers. Anatomically relevant throat models, such as the one developed by the OPC consortium, supplied by Amaze Consulting, have become widely used during in vitro testing due to the improved correlation between analytical lab data using this equipment and lung deposition as measured in a clinical setting. In this work, we developed a novel instrumented anatomical throat model based on the medium-sized Amaze design, produced it using SLA 3D printing, and instrumented it with 5 fine wire thermocouples. It is used as a diagnostic tool for temperature measurement within the oral cavity. An image and cross-section schematic of the instrumented throat are seen in the figures on the slide. During testing, placebo aerosols containing current and future propellants were fired into the throat using a Kindeva drug delivery actuator with 30 liters per minute of air co-flow. A CFC-based aerosol was harvested from a 3M Salbulin product and fired using the same actuator. Thermocouple voltages were amplified using bespoke equipment and digitized using a Kistler lab amp. The figure in the orange box shows the temperature profile of the plume measured in the middle of the oral cavity through time. the temperature profiles are all very similar in trend, showing an initial sharp drop in temperature as the cold, evaporating spray passes over the thermocouple. Mixing with entrained air promotes droplet evaporation, producing cold vapor in the plume. As evaporation ceases, the temperature recovers to ambient as further air is drawn in through the throat behind the plume. Minimum temperatures broadly follow the rank order of propellant saturation temperature, with HFA 227 being the warmest, followed by HFO 1234. The Salbuline CFC formulation was similar to HFA 134, but HFA 152 was slightly colder. The latent heat of vaporization and specific heat capacity properties of all the propellants vary. In the case of HFA 152, they are both much larger than those of HFA 134, and this could be a contributing factor to the differences seen. Here, the left figure in the orange box is the data from the previous slide, at the front of the oral cavity. The data in the blue box is the data measured at the back of the oral cavity. The shape of the temperature profiles for all propellants are similar between the front and the back of the oral cavity. However, the drop in minimum temperatures measured from the front to the back of the cavity shows that droplet evaporation, producing cold vapor which chills the plume, is still occurring as the plume travels through the oral cavity. Finally, the figure in the green box shows the temperature profile measured by a thermocouple on the surface of the tongue through time. The time-varying temperature profiles are again similar in trend, showing an initial sharp reduction in temperature as the cold, evaporating spray impacts on the tongue. The temperature drops are much larger than measured in the oral cavity itself, likely due to liquid impaction. Although the minimum temperatures are again broadly in line with rank order of propellant saturation temperatures, the HFA 152 and CFC formulations are both significantly colder than HFA 134, HFO 1234, and HFA 227. So to conclude, in this work, we have developed a novel instrumented version of the OPC anatomical throat model. It is used as a diagnostic tool allowing temperature measurement within the oral cavity during discharge of a pharmaceutical spray. We found, surveying current and potential future pMDI propellants, that HFA 227 had the overall warmest spray plume, and the coldest was HFA 152. HFA 152 is arguably the leading candidate replacement pMDI propellant. Given the importance of plume temperature to patient acceptability of pMDI products, as was seen during the CFC to HFA transition, the fact that HFA 152 recorded the coldest spray temperature warrants further investigations in this area. And with that, I thank you for taking the time to listen to our presentation and for your interest in our work.